My name is Melissa Heikkilä. I am the AI correspondent at the Financial Times and delighted to be joined by Yann LeCun, Chief AI Scientist at Meta and Professor at NYU. Now, Yann, every time I see you, you are out there launching some new AI model that is changing the way we think about AI. And this year it's V-JEPA 2. So, what is V-JEPA 2 and why is it a big deal?
Well, there's a V-JEPA V2 because there was a V-JEPA V1 a while back. Basically, it's a model that attempts to advance along at least three dimensions, three challenges of AI. The first one being AI systems that understand the physical world. The second one, systems that are capable of reasoning. And the third one, capable of planning. So those are three major obstacles or challenges that we need to kind of overcome to have AI systems that go to the next level. And so V-JEPA is one of the first systems that can really learn how the physical world behaves by being trained to predict videos, essentially, right? So show it a piece of a video and corrupt that video in some way. You can mask a piece of it. Or just mask the future, the second part of the video, or just a whole chunk of it, and then train a system to fill in the blanks, basically predict what is missing in the video. Now, we've been trying to do this for many years. In fact, this idea of this is a particular instance of self-supervised learning, and that's really what has powered the success of large language models. And we've been trying to work on this for video for 10 years. Actually even more, but and it's been a bit of a failure until recently. And the reason is that although it's easy to kind of predict the words that are going to follow a particular text, which is why LLMs are working so well, you can't do this with video. If you train a system, you show it a piece of video and you ask it to predict what comes next, there is no way you can predict all the details at the pixel level of what goes on in this video. And so the JEPA idea, that means Joint Embedding Predictive Architecture, and the V stands for video, basically does not even attempt to reconstruct pixels. It attempts to learn a representation, an abstract representation of the video, where a lot of the details are eliminated, so that the system can make predictions in that representation space. That's the basic idea of JEPA. And then we've been trying to apply this, sort of finding recipes to train those things, at the large scale, and apply this to sort of various domains, not just video, but just about everything.
The new thing is also you're using robotics data, so physical collections of physical data collected from how you animate work in a 3D world, right? So tell me, why is that significant?
Well, so that addresses the second challenge, machines that are capable of planning. So once the system has been trained just by watching video to basically predict what's missing in the video at the representation level, there's a second phase where you train what's called a world model. So a world model is something that tells you, given the state of the world at a particular time, that you can observe from a short clip of video, and given an action that you imagine a robot taking, could the system predict what the state of the world is going to be after the action has been taken? And so if you have this kind of world model, you can, a system that has this model of the world can imagine the consequence of a sequence of actions, and therefore can figure out a particular sequence of actions that will fulfill a goal, that will accomplish a task. That's planning. So that's one of the big challenges that AI systems should be able to do. And planning and reasoning are really the same thing, so this could give us a blueprint also for systems that are capable of reasoning. And what we've shown with V-JEPA V2 is that when we train such a world model, we can use it to basically plan the motions of a robot arm to grab an object or open a door or something of that type. Those are not particularly complicated tasks, but what's interesting about it is that the system can basically learn or can accomplish those tasks without being explicitly trained to do those tasks. It's just using its world model to predict what the consequences of its actions are going to be.
And what are the real-world use cases for this? Like, why do we need to build this and how can we use it?
So everybody is talking about AI systems that can reason AI systems that can plan, agentic systems that can take actions. To be able to take an action or a sequence of actions reliably, you have to be able to imagine what the result of those actions is going to be. If you take an action, a sequence of actions blindly and you don't know what the effect is going to be, you're going to make some mistakes. And so current systems, LLMs, don't have those internal world models. They're basically planning blindly by just kind of pretty much regurgitating plans they've been trained to do or produce. If you have this concept of world model, and a lot of people in AI are working on this at the moment, then the system can just project, imagine, what sequence of actions, what is going to be the effect of the sequence of actions, and then plan to accomplish a particular goal. Now, there's still a lot of challenges there on the way. It's not like we've solved the problem. And this approach also connects with some classical work in robotics, in motion planning. The difference here being that those world models are trained from data, and it's completely unsupervised. There is no labeled data or nothing like that.
Now, for AI scientists, one of the biggest goals is understanding machine intelligence, or creating it. This concept called artificial general intelligence, AGI. How does this get us to that?
Well, so I think so I don't like the phrase AGI, okay, because it's used to designate systems that have sort of human level intelligence, if you want. And so that relies on the assumption that human intelligence is general. And I'm sorry to say, human intelligence is not general at all. We're very specialized. Slightly more general than most animals, but some animals are smarter than us in certain areas, and certainly computers can solve certain tasks much better than we can. So that means in some way we are specialized, right? So I prefer these two phrases that we use at Meta. One is ASI. It's a little scary. It means artificial superintelligence. It means, okay, by the time that we get to human level intelligence, we can get past. And in fact, we already have a number of tasks where machines are already superior to humans. So that's what we should be talking about. And superintelligence doesn't mean it's general. It just means it's slightly better than humans in most domains. And then there's a second phrase that we use, and it's AMI. We actually pronounce it the French way, ami, which means friend. And that's basically our blueprint or plan to reach ASI. So there's a long-term plan in the company to basically produce AI assistants that are as smart as humans or perhaps better, that will help us in our daily lives. It's a challenge that we set for ourselves 10 years ago, and now, but it was really sort of exploratory research at the time, and now it's become more of a kind of a product strategy, if you want, even though we don't know how to do it yet. We're kind of starting to see the end of the tunnel, so it's becoming real. And so the AMI plan is a set of techniques that some of us have been working on to basically overcome those four challenges I was talking about. Systems that understand the physical world, have common sense, if you want, have persistent memory, can reason, can plan, and also a fifth one, which is systems that are controllable and safe. So basically you give them a task and they accomplish that task, and that's it. They don't do anything else.
Great, I'm glad you mentioned superintelligence, because this week there's been a lot of reports about Meta looking to start up a new superintelligence AI unit led by Scale's Alexander Wang. What's the plan there?
Well, I can't comment on electronic or whatever. This is being discussed, whatever. But what I can say is that the plan of FAIR, Fundamental AI Research, which is the sort of long-term research branch of Meta in AI, has always been to reach human intelligence and go beyond it. It's always been the plan when it was created 11.5 years ago. It's just that now we have kind of a clearer vision for how to accomplish this, and V-JEPA V2 is kind of a step in that direction, if you want. And so it's becoming so real now that it's kind of the ambition of the company to really kind of do this at a product level as well. So Mark Zuckerberg is seeing this as kind of an achievable goal, and that's that's why you hear this sentence being thrown around.
But concretely, what would superintelligence look like?
Well, okay, we already have a lot of AI systems that are better than us at many tasks, right? So you can buy a 30-euro gadget that plays chess and will beat you at chess, which means humans are not very good at playing chess. You know, similar for Go and poker, and you know, there's a number of games like this where computers are just better than humans. But it's also true of, I don't know, solving equations, computing integrals in mathematics, or you know, finding the best path in a map to go from one city to another, right? We're used to this. Like the machines are better than us at this. In fact, that's really what we should work on. Machines that are better than us at certain tasks for which we're not particularly good, right? That's the best way to assist humans with computers. That's actually the history of computers, really, using computers for things that humans are not particularly good at. So it's just a continuation of this, where, you know, in a future in which, like, all of us will be walking around with smart glasses or other smart devices, within which there will be AI assistants that we can talk to, we can ask any question, maybe they display informations in the glasses and things like that, and that will sort of amplify your intelligence if you want. It's like having a staff of really smart virtual people kind of working with you at all times. You know, all of us will be like, you know, a CEO or a minister or a university professor, you know, with a staff of students who are smarter than themselves. So, you know, it's empowering. A lot of people kind of feel threatened by it. I think it's really empowering to work with people or machines that are smarter than you.
Can you talk a bit about the work you're doing at FAIR? Because the team has gone through quite a lot of changes recently, right? Joel Pinot, the VP of AI Research, left this spring, and there's been a lot of reorg. So how is your work going to change, and what do you need to do to get to that vision?
Well, so it's not changing particularly. Yeah, Joel actually left just a few weeks ago. And the new person leading FAIR is Rob Fergus, who actually was one of my first hires at FAIR back 11 years ago. And then he spent 5 years at DeepMind and came back. So now he's leading FAIR, and it's basically an opportunity that we're seeing to sort of reboot FAIR towards the ambitious goal of AMI or ASI, and sort of, you know, plot a path for the more sort of product-oriented part of Meta to kind of follow, perhaps, to make progress towards human-level AI, essentially. So not that much of a reorganization, really.
Sorry?
There's not much of a reorganization other than a change of leadership, but other than that, our mission stays the same.
And so what would that concretely look like for a company like Meta? Is it products other than chatbots, or what?
Well, I mean, there's chatbots, right? We're used to them now. We want systems of this type that are agentic, so they can sort of, you know, act in the digital world, at least. We want perhaps systems that have a mental model of the user they're talking to, so they're not telling us things that we already know or that we're not able to absorb, right? So those systems will have to have some mental model of what we know, what we don't know, you know, what we are capable of digesting, what kind of information we could be interested in. And systems that can, you know, plan sequences of actions that might be complicated, you know, making reservations for, you know, travel and stuff like that. And then eventually also kind of similar things for the physical world. Domestic robots, robots of various types, and Meta is actually getting involved in robotics in sort of a big way. And then in between there are things like code writing, okay? So we have systems, I mean, it's probably one of the biggest applications of LLMs at the moment is helping software developers write code. And there is one issue with this, which is that very often when the code is produced, it's globally maybe correct, but not completely correct. You have to kind of fix some bugs and kind of change a few things. And those are generally relatively simple pieces of code, right? You can't ask a system to design a new algorithms or figure out a data structure for a particular problem that they've never seen before. They're basically kind of regurgitating code they've seen, you know, over the corpus that they've been trained on. What we want is, and that's what we're working on, a system that can imagine what the result of executing an instruction or making a function call will cause to the state of the program, and then plan a sequence of instructions to arrive at a particular goal. So it's very similar problem that I was talking about earlier, the ability to plan, to imagine what the consequences of your actions are. That's required for dialogue systems, for agentic systems, for code generation, and certainly for physical robots.
Yeah, if only humans can do that too. What's your vision for FAIR, right? Like the AI field is so competitive and it's a constant talent war. How are you making Meta's AI research stand out and positioning yourself in the market?
Well, I think the plan that we are following for AMI, for Advanced Machine Intelligence, using those JEPA architectures and architectures that are capable of planning and reasoning, all that stuff, I think it's pretty original. I wrote sort of a vision paper that I published 3 years ago. I put online saying, like, here is where I think AI research should go over the next 10 years. This was before ChatGPT, right? And it hasn't changed significantly in the details, yes. And since in the last 5-6 years, we've been sort of making steady progress along this plan, basically. V-JEPA is just the latest incarnation of this. And so we're clearly making progress on those systems. Now, here's what's interesting. Those architectures, the JEPA architectures, are not generative architectures because they don't try to reconstruct or predict the world that they are trained on, the data that they are directly trained on. They are trying to learn an abstract representation, and they make prediction in that abstract representation space. So those architectures are not generative. Okay. Now, this is our long-term plan. This is what we are betting, quite a bit on at the research level. That doesn't mean that the current paradigm of LLM is not useful. There's obviously a lot of applications of LLMs that need to be developed, that are being developed. Foundation models that need to be open source. We're very big on open source at Meta, as you know. So it's not because you believe that reaching human-level intelligence requires a new paradigm like JEPA that you necessarily believe that LLMs are not useful. They're useful. We should be working on them. We are working on them. But it's a shorter term, and FAIR has always been kind of 3, 5, or 10 years ahead of the current fashion in AI. So that's still what we're working on. We have our eyes on the horizon.
And what sort of timeline are you looking at for superintelligence?
Yeah, that's a trick question, right? I mean, generations of AI researchers have been consistently wrong about this kind of estimate. So, okay, my story would be if all the planets lined up, if all the techniques that we are imagining developing work out, we're encountering the kind of usual difficulties in developing them and scaling them, we're going to have a good handle on whether this kind of JEPA approach is really going to take us there within 3 years. And then within 5 years, probably some early results or prototypes that may have systems that really understand the physical world, perhaps at the level of a cat or a rat or something like this, right? And then we're going to work our way up towards systems that can also plan not just in the sort of low-level physical world, but also in sort of abstract domains, perhaps connected with language or connected with mathematics or with geometry or things like that, right? And maybe reach human intelligence at some point, but it's almost certainly harder than we think. That doesn't mean we're not going to have useful, artifacts on the way to there. So I think we're going to start seeing kind of the more tangible applications of this maybe within 5 years or so.
Okay, and what do the next 6 months look like for Meta AI? The next 6 months.
Next 6 months. For us, we have like a plan of like so many problems to solve that we think we can solve, but we really need to work on them, right? So the V-JEPA V2 is one of the JEPA architectures that's trained in a particular way on videos, and we can train them on, I think the amount of training we've done is like 1 million videos or something. It's a lot. So we can scale those models, we can scale the training, that's at least what we can demonstrate. We can show that we can use those models to plan simple actions for robots. Then we have to apply this to kind of more situations. But also, we don't think we have the perfect recipe yet. Like, we think there is probably a better way of training those JEPA architectures that we haven't figured out yet. So there's some work going on this. There are technical problems linked with planning. So when you plan a sequence of actions, and it's true for humans as well, we can't plan a very long sequence of actions. If it's a complicated task that requires many actions, we need to plan hierarchically. And this is a completely unsolved problem. So let's say I'm sitting in my office at NYU, and I want to be in Paris. I want to fly to Paris, right? So I cannot plan my entire trip to Paris in terms of millisecond by millisecond muscle control, which is really the low-level actions I can take. I have to plan this trip at a very abstract high level. And at high level, I can say, oh, I need to go to the airport and catch a plane. And I don't need to know the details, I don't need to know how bad the traffic is or how I'm going to get to the airport, I just need to go to the airport. So now I have a sub-goal, going to the airport. I can plan a sequence of actions to get to the airport. I'm in New York, so I walk down on the street and hail a taxi. How do I walk down on the street? That's another sub-goal. Well, I need to get to the elevator, push the button, go down and walk out the building. How do I go to the elevator? I need to stand up from my chair, pick up my bag, open the door, walk to the elevator, avoid the obstacles and things like this. And it gets to a level where I have all the information I need to be able to take the action. Right? So this idea that we're doing, everything we do, we plan hierarchically, is very powerful. We don't know how to do this with AI systems yet. We have some ideas, but it's still very much at the research level, and that's a big challenge to crack again for the next few years.
I know we're in time, but what is your intuition? How do we do that?
Well, we hire smart people. We, give them the problem, try to convince them that this is an interesting problem to work on, because most scientists and researchers have their own idea about what is a good idea to work on, so you can't really tell what to work on. You can do this with graduate students, though, so that's a good way to start. And then you try to kind of socialize this idea with other people so that they give you an idea about perhaps how to approach that problem. So the problem of planning, for example, there's a lot of very deep sort of questions that have to do with applied mathematics in there, not more than computer science, really. So you have to go talk to applied mathematicians and tell them, we have this problem that we don't know how to solve. It's an optimization problem. You guys have been working on this for 20 years, not necessarily for planning, but can you help us solve this problem? And it takes a whole scientific community, which is why it is very important to practice open research, because you need contribution. This is a scientific problem, it's not a technological development problem. You need to basically kind of gather all the talents that may contribute to this from the scientific community, in academia, in other companies, and public research, particularly in Europe. So that's why we need to practice open research. And then the outcome of this is that we open source our code. So V-JEPA v2 is open source.
That's a fantastic note to end on. Thank you so much, Yann. That was fascinating. And thank you so much for joining us today.
Thank you.